Hello students, welcome to today's session of chemistry. As you all know, we have started study of 7th lesson of your syllabus, that is modern periodic table. Before starting today's session, we will just revise what we learned in the previous session. In the previous session, we learned about the electronic configuration in periods. What is electronic configuration? It is the arrangement of electrons in various shells, subshells and orbitals, we can say. We know there are 7 periods in the periodic table. Along a period, if we move from left to right, the atomic number increases by 1. And every time 1 electron is added to the outermost shell. Every period ends with complete octet configuration of the valence shell, and the next period begins with addition of electron to the next shell of higher energy compared to the previous period. The first shell thus gets filled along the first period, as the first shell has only one subshell, that is S. That means it has only one orbital, hence it has a capacity to accommodate only 2 electrons. Hence there are 2 elements in the first period, that is hydrogen and helium. Now, the second shell, electrons are again filled as we move from the left to right every time 1 electron is added. The second period thus begins with lithium and ends up with neon, that means 8 electrons. The capacity of second shell is to accommodate 8 electrons. Hence, there are 8 elements in the second period. Likewise, there are 8 elements in the third period as well. So, we have seen in detail about the electronic configuration in periods. Now, in today's session, we are going to see about the electronic configuration in groups. In case of periods, we can say in short that a period begins by filling up of 1 electron to the S subshell of a new shell and ends with an element having complete octet corresponding to the same shell. Between these two ends corresponding to S and P subshell of the valence shell, the inner subshells D and F are also successively filled. Now, about the electronic configuration in groups. Let us begin with. If we move down any group, a new shell is added. As we move down the group, a new shell is added. The general outer electronic configuration, therefore, is expected to be the same down any particular group. We are now going to consider about the groups. If we take one group, that is group number 1, there are 7 periods, that means there are 7 elements. As we move down the group, every time you will see that a new shell is added. Now, this is true for the groups 1, 2 and 3. Now, this is group first, and along with it, first, second and third groups are there. If we move down any group from first element to last, the first element is hydrogen with atomic number 1. What will be the electronic configuration? 1s1. For lithium, it will be 1s2, 2s1. For sodium, atomic number 11, 1s2, 3s1. For potassium, it will be 1s2, 4s1. Rubidium 5s1, cesium 6s1 and francium 7s1. So, down the group, every time a new shell is added with S subshell having 1 electron for the first group. These are called alkali metals. These are strong metals. All of them have 1 electron in the outermost shell. Outermost shell is called nth shell. That is principal quantum number. nth shell with s subshell having one electron that constitutes group number 1. That means all of them have common general outer electronic configuration, which will be nth ns1. It is written like this, ns1. Now, if we consider second group, beryllium, atomic number 4, then it will be 1s2, 2s2. Magnesium 12, 1s2, 2s2, 2p6, 3s2. Calcium 4s2, strontium 5s2, barium 6s2, radium 7s2. So, second group elements have outer electronic configuration as ns2. ns2. Now, if we move to third group, Sc, scandium, it has atomic number 21. That means it has outer electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6. After that, 4s2, 3d1. 3d1. After 4s, 3d will be filled, because the rule is the energy, it is called above principle. It tells us that orbital with lower energy will be filled first and then with the higher energy. And 4s has less energy than that of 3d. Hence 4s will be filled first and then comes 3d. That means nth shell is called ultimate shell or the outermost shell. Before that comes penultimate shell, and d is always penultimate. Hence it is called n minus 1d shell. When 4s2, then comes 3d1. That means nth shell will be 4 and n minus 1 will be 3. When it comes to f subshell, then it will be n minus 2f. n minus 2f. That means it is pre-penultimate shell. How? We will see when we come to a block. So this is all about first three groups. That means 1, 2, 3 groups, they have general outer electronic configuration every time a new shell is added as we move down the group. Now, in the groups 13 to 18, that means P block. First the D and F, which are n minus 1 and n minus 2f, they are completely filled, and the general outer electronic configuration is same down the group 13 to 18. So, if we write the electronic configuration of the elements in group 13 to 18, then it will be almost same outer electronic configuration. Suppose, for example, we will take the example of 13th group, boron, atomic number 5. That means 1s2, 2s2, 2p1. Aluminium 13, 1s2, 2s2, 2p6, 3s2, 3p1. Gallium will be 4p1, indium will be 5p1. Like that, if we move down the group, 13th group, the outer electronic configuration will be ns2 np1. ns2 last shell, s complete with 1 electron in p subshell, because boron is 2s2 2p1, aluminum is 3s2 3p1. Understood? So, same way, 14th group, carbon 6, that means 1s2, 2s2, 2p2, 2s2, 2p2, ns2, np2 we can say. Like that, silicon 3s2, 3p2, germanium 4s2, 4p2. Like that, 14th group has general outer electronic configuration as ns2, np2. 15th has ns2, np3. 16th ns2, np4. 17th will be ns2, np5. And the last group, that is noble gases, it will be ns2, np6, complete octet. And hence they have stable outer electronic configuration. Understood? So, down the group, every time a new shell is added, but the general outer electronic configuration is same. That means that contains same number of electrons. Now, if we consider the groups of D block, that is 4 to 12, there is some variation in the general outer electronic configuration only at the latter stage when D and F are introduced, that is observed in D block elements 4 to 12. We will see that when we consider about the D block. Okay, so this is all about the groups 13 to 18. Now we will take a look at a table that will show you general outer electronic configuration of group 1 to 3 as well as 13 to 18. As I told you, first group, those are alkali metals, general outer electronic configuration will be NS1, lithium with 2S1, sodium with 3S1, like that. In the same way, group 2 has NS2 electronic configuration and beryllium with 2S2, magnesium with 3S2. Group 3, NS2 N-1 D1, because third group is in the D block. So D will be that will be filled one by one. Same with 13 group, NS2 NP1, NS2 NP2, P block starts at 13. So P subshell will start filling up in P block. So NP1, NP2, NP3, NP4, and when we come to 18th group, that will be NS2 NP6, complete octet. So this is all about electronic configuration in groups. So down the group, if we go, a new shell is added. Hence the general outer electronic configuration is same down any particular group. And hence we are going to see that they show almost similar chemical properties. Now we will consider the electronic configuration in the 4 blocks. We will see one by one. The structure of modern periodic table has 4 blocks. You know them very well. The blocks are named according to the subshell in which the last electron enters. That means again we have to write the electronic configuration, and if the last electron is in S subshell, then that is S block element. Any element in the P block, pick up that, write down the electronic configuration. You will observe that the last electron enters P subshell. That means the blocks or the arrangement of modern periodic table in 4 blocks is based on that the element in the particular block has last electron in the same subshell. Now, there are 4 blocks. They are S, P, D and F. You know them very well. Now, we will start one by one. For example, first block, that is S block. The definition also will be done like this. If the last electron enters in the S subshell, then it is a S block element. That means the last electron is always in the S block. The S block has only one orientation. It is spherical in shape. It has only one orientation, or it has only one orbital, we can say. An orbital can accommodate maximum 2 electrons. Hence, if you see, there are only 2 groups in S block, because S has a capacity to accommodate 2 electrons only. Hence, there are 2 groups, first and second, in S block. And the general outer electronic configuration, if we see, that will be NS1 to 2. NS, first group NS1, second group NS2. So, NS1-2 it is written. That is 1 to 2. That constitutes S block. So, general nth shell will be ultimate shell. The ultimate shell with S subshell with either 1 or 2 electrons will be S block. Thus, elements of group 1 and group 2 belong to S block. It is present to the extreme left of the modern periodic table. This is S block with 2 groups. First group is called alkali metals with general outer electronic configuration NS1. Second group NS2. General of S block NS1 to 2. Now, second block is P block. It has 6 groups. If the last electron is filled in the P subshell, that element belongs to P block. As you know, P block or P subshell has 3 different orientations, or we can say 3 orbitals are there in the P subshell. Hence, P has a capacity to accommodate 6 electrons. Hence, there are 6 groups in P block from 13 to 18. Together they constitute or they form p block. The p block is there, which is placed to the extreme right of the modern periodic table. It ends at group 18, that is the family of inert gases or noble gases, because they have completed octet. The first element of the group 18, one exception is there. Helium, if we write the electronic configuration of helium atomic number 2, the electronic configuration will be 1s2. Last electron is not in the p subshell, but still it is placed in the p block because it is inert gas. So it belongs to family of noble gases or group 18. Hence it is placed in the p block. It is exception. Now, the 18th group elements have completed electronic configuration, or their valence shell is completely filled with 6 or together 8 electrons, or we can say the octet is complete. Hence, the general electronic configuration of p block elements will be ns2, nth shell with s complete, and p starts filling up from 1 to 6. Hence, 13th group has ns2 np1 and 18th group has ns2 np6. Hence, generally it is written as ns2 np1 to 6. That will be the general outer electronic configuration of p block elements. 13 will be ns2 np1 and 18 will be ns2 np6. Now, third block, d block, where it is located? It is at the center, in between s and p block. D block, again the definition. When the last electron enters D subshell, that element belongs to D block. The energy of ns orbital is less than that of n-1 d orbital. Hence, the last electron enters n-1 d only after ns subshell is completely filled. That means after 4s, 3d is filled. After 5s, 4d is filled. After 6s, 5d is filled. Like that. So after ns subshell, n-1 d subshell starts filling. And when it is complete, then d block is complete. Now, there are 5 orbitals in d subshell. We have seen it last session also. There are 5 different orientations, 5 orbitals are in the d subshell. Hence, d has a capacity to accommodate 10 electrons. Hence, there are 10 groups which start filling from ns to n-1 d1 to n-1 d10. And the 10 groups are from 3 to 12, which are at the center between S and P block of the modern periodic table. What will be the general outer electronic configuration then? ns to n-1 d 1 to 10. It should be like that only. But I have written here ns 0 to 2. There are some exceptions related to the extra stability of the electronic configuration. Hence, sometimes ns 0 to 2 electronic configuration is observed in some cases. That's why I have written like that. ns 0 to 2. Sometimes ns 0, sometimes ns 1, sometimes ns 2. Accordingly, the electrons in the n-1 d subshell are adjusted to get extra stability. So, some variations in the configuration. It is written here like that. As a result of extra stability associated with the half filled and fully filled subshell are observed. Half filled, that means D has a capacity to accommodate 10 electrons. But when there are exactly 5 electrons in the D subshell, that means all the orbitals with 1 electron each are filled, that gets extra stability. And to achieve that extra stability, S electrons move to D electrons, and that's why ns gets less than 2 electrons and n-1 d gets 5 electrons. And that is observed in some cases. For example, if we see the element chromium with atomic number 24, it should have electronic configuration 4s2 3d4. But when 3d5 will be the electronic configuration, chromium will be more stable. And to achieve that stability, one electron from the s subshell moves to the d subshell. And hence the electronic configuration is 4d1 3d5 and not 4s1 3d5 and not 4s2 3d4. So one electron from s is moved or jumped to the next immediate energy level, that is 3d, and it becomes 3d5. So this is variation. Hence the general outer electronic configuration of d block is ns 0 to 2 n minus 1 d 1 to 10. So this is d block from 3 to 12, and if we write the electronic configuration for the scandium first member 21, it will have the electronic configuration as ns2, ns cell will be, now 21 will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1 will be scandium, and 4s2, 3d10 will be zinc. 5s2, 4d1 will be Y, the 39 yttrium it is, and 5s2, 4d10 will be cadmium with 48 atomic number. Understood? So ns 0 to 2, n minus 1 d 1 to 10 will be the outer electronic configuration of d block elements. What about a block? A block, as you know, the last electron, the same definition. The last electron is filled in f orbital, and there are 7 orientations or 7 orbitals in f subshell. Hence, f has a capacity to accommodate 14 electrons. Hence, the general outer electronic configuration of f will be, it is somewhat different. ns2, n shell will be ultimate, final shell. n minus 1 d 0 to 1 and n minus 2 f 1 to 14. That will be the outer electronic configuration of f block elements. A block, as we know, where it is there, it is placed below periodic table in 2 horizontal rows containing 14 elements each, because there are 4f and 5f sublevels. 4f will be filled when 5d and 6s is filled. 6s has less energy than 5d and 5d has less energy than 4f. Hence, when 4f starts filling up, before that 5d and 6s are already filled. Again, I have written here 0 or 1, n minus 1d 0 or 1. Again, that is to achieve extra stability. When f will get exactly 7 electrons, it will get extra stability. And to achieve that, sometimes 1 electron from d subshell moves to f. Why it is d 0 to 1? Because f block elements are there in the first group of d block. You know that. In the which period we have introduced a block? In the 6th period, there are lanthanides, and in the 7th period, there are actinoids. The lanthanides are there, they are in the 6th period and 3rd group, while actinoids are in the 7th period and 3rd group. And hence, D will get either 0 or 1 electrons. Actually, it should get 1 electron, but to achieve extra stability, sometimes it gets 0 electron. Hence, the outer electronic configuration, if we write of one element, that is europium, it is exception again. You will get 6s2, 4f7, 5d0. Actually, 4f6, 5d1, 5d1 should be the electronic configuration. But to get half filled, exactly half filled, f subshell, d electron moves to f subshell. And instead of 6s2, 4f6, 5d1, it gets for 6s2, 4f7, 5d0. Otherwise, generally ns2, n minus 1 d1, n minus 2 f 1 to 14 will be the electronic configuration of f block element. This f block As you know, there are 14 elements, as already I have told you, lanthanides and actinides, 14 elements in each series. If you see, this is a block. The first member is actually cerium. Lanthanum is there in the D block. Lanthanum is D block element. But after lanthanum comes cerium, and there are 14 elements. After lanthanum are called lanthanides, and after actinum, hence they are called actinoids. So cerium, the first member, they have electronic configuration 6s2, 5d1 and 4f1. And the last member lutetium is 6s2, 5d1 and 4f14. Like that, thorium will be the after actinum, that is actinoid, first actinoid with atomic number 90. The electronic configuration will be 7s2, 6d1, 5f1. And lawrencium, the last member of F block with atomic number 103, the electronic configuration will be 7s2, 6d1 and 5f14. So this is all about the electronic configuration in 4 blocks S, P, D and F. Understood? So in general we can say that along a group, if we move down from top to bottom, they all of them show same general outer electronic configuration. That means same number of electrons are there in the outermost shell. While all the blocks S, P, D and F blocks have elements according to the entry of last electron in the corresponding subshell. If it enters S subshell, then it is S block element, likewise. Understood? Now, what will be the assignment for today? Write general electronic configuration for all the blocks S, P, D and F. As well as you have to write the outer electronic configuration of groups 1 to 3 and 13 to 18. That means S as well as P block elements. That I haven't written, but you have to write in a tabular form that is given on page number 97 of your textbook. So this is all about today. Thank you.